So in this numerical we have the stresses on an element are 100 megapascal tensile and shear stress of 40 megapascal in clockwise direction. Find the normal shear and resultant stress at a plane inclined at 35 degree to the normal stress, right? So this is the different type of numerical. Let us start solution. Just copy this. Given it is 100 megapascal tensile. So just change this 100 megapascal tensile. So it is positive. I don't have sigma y, but this is tau xy. It is shear stress. So it is tau xy is 40 megapascal clockwise. So that will be positive 40 megapascal. Theta is 35 degree. So 2 theta will be 35 into 2, 70 degree. Now you have to draw a line, horizontal line of 100 megapascal only. So I can take full scale in this, right? So let us take full scale. Scale 1 mm, sorry, 1 mm is equal to 1 megapascal. Alright, now let me go back here. First of all, draw a horizontal line, which I have already done, and on this I will mark a point. What do I call that as O, right? So this is my O here. Let me just zoom it a bit. Now from O, I have to draw a line which is representing my sigma x, right? So sigma x is 100 megapascal. Since 1 megapascal is equal to 1 millimeter, 100 megapascal will be 100 millimeter. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is my OJ, correct? OJ represents the major normal stress. So I am using same notations so that it is easy for us to remember. Now this is representing the sigma x, right? You have to dimension this. I am not showing all those things. Please do that. Now the shear stress is 40 megapascal and it is positive. Since it is clockwise, it is positive. Whenever you have positive shear stress, you have to draw it on the draw it above this horizontal line, right? The shear stress is always perpendicular lines. So 40 means 40 millimeters. 40 megapascal is 40 millimeters. So this is 1, 2, 3, 4. So this point will be my shear stress point. So let me just call this as E, right? Capital. Because this point is not, you are not going to use this for any calculation of stress. So I'm just keeping that as E. And I will draw a line also of maybe different color. I'll use a black line from here to this point, right? Now this is representing my EJ is the shear stress. Since it is positive, that is why it is above. Now on the inclined plane, there is a resistive shear stress which is in opposite direction. So I have to draw another line from O in opposite direction. So that will be again 40 megapascal. So one, this is one, two, three, four. I think the line has got some maybe little below this, right? There is some problem with that grid there. So it should be equal. One, two, three, four. I think I got it right. Right? So both should be equal. And then let me call this point as uh, B. Right? I call that point as B. Now you join ED. So from here, right, and this point here. Now this ED is actually bisecting this line OJ at this point, right? So I'll call that point as C. Now you have to draw a circle with CD or CE as radius. You draw a circle here. So let me try to do that. Yes, right. I think there is some problem with the grid, so that's why you should get equal distance on this side and this side, right? Here it is slightly messed up. You should get it properly if you are done. Right? Now after drawing this circle, I have to now draw the inclined plane at an angle of 2 theta. Now theta is 35 degrees, 2 theta is 70 degrees. See, in our previous numerical, we took this as the reference. Now DE is my reference line, right? So DC, CD is the zero angle. Now from CD you have to measure 70 degree. Now let me just do that. If this is C, now this is approximately 90 degree. So I have to decrease 20 degree means somewhere here, right? So this angle is 2 theta. Let me just show that. So this is 70 degree. All right, and I'll call this point as P. Okay, now from P you draw a perpendicular line. You draw a perpendicular line like this. So this point is Q. Okay, and just move this here. So this is Q. This is O. Now OP gives you the resultant stress. PQ gives the shear stress, and OQ gives the OP is the resultant, OQ is the normal stress, and PQ is the shear stress, right? So this is not drawn to scale properly. This angle, I'm not sure, so I'm getting something like this, but we should be able to get it properly. Okay, so let me go back here. I have drawn this here, right? So I have drawn this here. We can measure it from this. Let me just measure these things. This is O, this is P, this is Q, right? So first I will measure the normal stress, that is OQ. Now OQ is very small here, so from here to here it is 4.688 or 4.69. I'll just copy this. How much is that? 4.7 mm. Since I have taken 1 megapascal is equal to 1 mm, so this will be 4.7 megapascal. Okay. Then shear stress is PQ. This is PQ, this vertical line. So this is 33.3 millimeter. 33.3 mm. So that is equal to 33.3 megapascal. The resultant stress, this is O and this is P. So from here to here, okay, I should have drawn a line there. This is 33.6 millimeter. 6 millimeter. So that is equal to 33.6 megapascal. Right? So this is how you will get the diagram. Is this clear? Any doubts or question on this?
No, sir.
All right.